Back. I would like to start with thanking the organizers, Professor Sunil Kumar, Rajesh, Dilip and others for inviting me to be a part of this symposium. I'm extremely honored and humbled to be here. So my group at IIT Kanpur focuses on experimental investigation of variety of soft matter materials, including colloidal suspensions, polymers, and we have been active in the area of artificial swimmers as well. These are entities which can extract energy from their surrounding and use them to self-propel themselves. And in this process, they remain overall force-free while doing the autonomous motion. Their motion somehow sort of resembles the motion demonstrated by biological microorganisms such as E. coli, which is a very commonly known bacteria. And since we are talking about particles or swimmers which are of micron length scale, we are dealing with very low Reynolds number, and hence the mechanism these swimmers they have to utilize in order to self-propel is a symmetry breaking mechanism. In biological swimmers such as E. coli, what they use is the motion of their bundle of flagella. For example, E. coli has this bundle of flagella attached to its body. It performs mechanical strokes which are asymmetric in nature, and through that it is able to break the symmetry that is required to self-propel. On the other hand, our focus is on chemical microswimmers. So what they do is they utilize a chemistry route rather to generate this asymmetry, and utilizing this chemistry route, they generate an asymmetric interaction with their surrounding media. Right? So there are two popular choices in terms of chemical microswimmers, artificial microswimmers. The first ones are these active genus colloids. So these are typical colloidal particles which have a patch of a different material on them. And because of this asymmetric chemical composition inbuilt in their system, they are able to generate a reaction which is also asymmetric, and hence they are able to interact with the surrounding in a symmetric manner, which is critical for their self-propulsion. The other popular system and the focus of today's talk are these active droplets. These are self-propelled droplets. They interestingly do not have any inbuilt asymmetry in them. So what is their mechanism of self-propulsion? I'm going to talk about that in a minute. Now, as engineers, we always have to propose some potential applications, because without that we will not get any students. So artificial swimmers carry several applications. They can be used to understand and model biological processes. They can be used to understand the collective behavior that we typically see in biological organisms. In terms of other applications, they have potential to be used in drug deliveries, biodiagnostics and others. Right? So with this all, we are also interested in these particular set of systems. Okay, so self-propelled droplets. These are typically droplets of one immiscible fluid in another immiscible fluid, and to keep them stable, we need to add surfactants to it. Right? But once we add surfactants just below the CMC, that is critical micellar concentration, these droplets will not do anything. They will remain stable. And if the size is very small, they will do Brownian motion. If the size is large, they will do nothing. But we make them active through a process known as micellar solubilization. So what we do is we add a lot of surfactant in the system, typically significantly beyond the critical micellar concentration. Then what happens is that this droplet encounters an empty micelle, a free micelle. In this collision, the droplet gives a part away to the empty micelle. Or I can say the micelle that collides with the droplet takes a part of the droplet away and leads to the solubilization of the droplet. And in this process, the micelle that collided as an empty micelle, but when it leaves as a filled micelle or a tiny nano droplet. Because the size of the micelle has to be increased because of the solubilization, it borrows some surfactant from the droplet interface, and this leads to a spontaneous generation of asymmetry in the droplet surfactant concentration coverage. That leads to a spontaneous gradient in the surface tension and generation of Marangoni stresses, which generates the interfacial flow from regions of low interfacial tension towards high interfacial tension. So the yellow colored are the filled micelles, which have a part of oil in them, whereas the empty ones are just the bare micelles. So the interfacial flow then leads to the droplet motion in the opposite direction, because remember these are overall force free system. So to balance the overall linear momentum, the droplets get propelled in the opposite direction. Right? So this is the mechanism that I'm going to talk about today. So using this system, this mechanism, yes.
Molecules don't grow beyond a critical size. You demonstrated that it's all of this roughly the same size. So when they solubilize.
Yes, they solubilize and they leave and remain more of the same size.
But during the solubilization process also, it's roughly oil drops of the same size that come out. Like in the picture that you shown, the nano droplets that come out.
These. So we do not have the capability to measure their size, right? All we can measure is the size of this big droplet. Yeah. So what in our lab, what we have used is we have used 5 Cb liquid crystals as the oil phase, and we have suspended these droplets in water with T-tab as surfactants, and then we have added variety of solutes to understand their effects, right? So once we have the system in place, we see very beautiful active motion, self-propelled motion of these droplets, and we also added some sort of dye in the droplets to visualize a trail of filled missiles, and in this video I'm showing you this very nice beautiful trail of filled missiles which these droplets leave in their wake while they are trying to self-propel. Another thing is that once the droplet starts to move, it gets a fresh supply of surfactant from the front, which provides a feedback to the droplet micellar solubilization. So as far as you have enough surfactant present in the system, once the droplet gets to propel, it will continue its motion for a very, very long time. Okay. So before I go to discuss our findings of the motion in polymeric solution, I would like to just give you an update. What do we know in terms of? So once the droplet starts to move in a particular direction, initially the surfactant is present anywhere. So the initial collision can start in any random direction. But once the droplet starts to move in a particular direction, it will get more supply of surfactant from the front. That is spontaneous, yes. So that depends on the local concentration fluctuations, and that varies from if you take the system with a smaller droplet size or bigger droplet size. Typically what we have seen is that bigger droplet size will undergo fluctuations more easily, and a smaller droplet will maintain the direction slightly longer.
There is no steady state. The system will
Eventually wants to equilibrate, and that state will be achieved once the complete droplet has been solubilized. Yeah, please.
But when it gets there, is the mobility going to be constant? Is the velocity constant as it keeps solubilizing? Or the persistence time? Are those quantities constant as it slows down and eventually none of those are?
So I didn't get your question.
So it's constantly losing out.
Correct. So typically what we observed is that for a reasonable size range that we have worked with, the rate of solubilization remains constant. Okay, but the speed changes because that depends on the size. So in Newtonian environments, what we know so far is that once we look at the droplets motion for a very long time, at short times we see a ballistic motion which is expected, but at long times because of concentration fluctuations, as Professor Gupta just asked, there are direction fluctuations that we observe, and at long times the motion becomes random in nature. Right? With increasing surfactant concentration, we see an increase in droplets self-propelled speed. So we can say surfactant concentration acts as a fuel for the system. There is a very popular behavior that these droplets demonstrate, which is resemble with the biological organism, that is chemotaxis and negative chemotaxis. So if you take a pool of surfactant, keep it at a particular place, that will generate a concentration gradient for the droplets, and we see that the droplets preferentially migrate towards the region of higher surfactant concentration, which is known as chemotaxis. And it is also demonstrated that these droplets will try to steer away from regions which are low in surfactant concentration, or I can argue they will try to steer away from regions which are rich in filled missiles concentration. Right? So that behavior is known as negative chemotaxis. Last year in a very exciting work, what we demonstrated was that if we put these droplets in an external flow, then these droplets can actually migrate upstream and perform a behavior known as rheotaxis. And we demonstrated that by manipulating the external flow conditions, the flow rate, we can actually control the droplet motion. In fact, we can go ahead and trap the droplet at a particular location also by just adjusting the external flow rate. Right? In all these behaviors that I just talked about in Newtonian environments. We are talking about capillary number which is typically very low, so we do not observe any shape deformations. So droplets maintain their spherical shape. Okay. Now, to understand what will be the effect of external macromolecular solutes, which is polymeric solutes, first we started with a control case where we added molecular solutes just to increase the viscosity of the system. So what I am showing here is trajectories that we observed in a series of systems where our goal was to increase the viscosity. So we added glycerol as a molecular solute, and what we observe is that as we increase the glycerol concentration, which resulted in an increase in viscosity going from 1 centipoise to all the way to 45 centipoise, the trajectory of the droplet becomes more and more jittery. So we started with a smooth looking trajectory in water, and with increasing glycerol concentration it became extremely jittery, which was sort of counterintuitive, because when we are increasing the viscosity of the system, we would expect the rotational motion to be suppressed. Rather, what we are observing here is that the motion becomes more and more jittery. We also noticed that with increasing glycerol concentration, the speed of the droplets was increased, and as I said, the motion became more jittery, so the persistent length of this droplets behavior was also continuously decreased. Right? So what we conclude from here is that despite increase in viscosity, what we observe is that the jitteriness in the motion is increased as well as the droplet speed is increased. Now from our understanding of these systems, we know that the droplet speed depends on the rate of solubilization. Right? So if you have a higher rate of solubilization, one can expect a higher droplet speed as well. So to confirm this, we evaluated the rate of solubilization of droplet in all these different systems, and what we found was that with increasing glycerol concentration, the rate of solubilization of the system also increased. Right? So we have two conclusions in front of us, that probably the increase in rate of solubilization can lead to this jitteriness in the behavior, or it could be effect of viscosity. So to conclude that, then we decided to use a macromolecular solute instead of just a molecular solute, which was glycerol. So then what we did was we added different molecular weights of PEO, which is polyethylene oxide, into the water instead of glycerol now. So we first started with 35 kDa molecular weight of PEO and 100 kDa molecular weight of PEO, and the concentration of these polymers was chosen such that we get the bulk phase viscosity to be nearly same as the glycerol system viscosity. So glycerol system viscosity was around 32 millipascal. So we added polymers such that we get roughly similar viscosity, and here we observe is that at 35 kDa and 100 kDa we do get jitteriness in the motion. Right? But the important thing is that although the viscosity is more or less similar, but the rate of solubilization in polymeric system is actually similar to water. Okay? Then what we did was we increased the molecular weight even further. So then we increased the molecular weight from 100 kDa to 600,000 kDa, and sorry for the typo, this is 8,000 kDa. Now what we see is that again the viscosity is roughly similar to the viscosity as the glycerol system. The rate of solubilization is similar to the rate of solubilization of water, but there is no jitteriness in the system at all, and the trajectories are more smooth in nature. Right? So that tells us that neither viscosity alone or the rate of solubilization of the systems alone can explain the jitteriness that we observe in the motion of these droplets. So to find the answer to this question, we came across this beautiful work by Michelin and co-workers, who proposed that the advection of the filled missiles in terms of the rate of solubilization that we have and the diffusion, their corresponding diffusion, these competing mechanisms can actually govern the mode of the droplet motion. So they characterize this competing mechanism through the calculation of a Peclet number associated with the droplet, and they propose that with increasing Peclet number, once we have a regime where the diffusion of the system dominates, diffusion of the missiles that are there in the dominates, then the droplet can get dynamically arrested, and that can lead to the jittery motion. It can explain the jittery motion. So to confirm this, what we did was we calculated the Peclet number of our droplets using D, which is the diffusion of filled missiles calculated from the Stokes-Einstein relation, where we used viscosity as the bulk viscosity of the system, and when we plotted the persistent length versus this Peclet number, we do not observe any dependence at all. Right? So that was a big surprise to us, because we expected this Peclet number to explain, because it has been proposed in literature earlier as well. Then what we did was, we decided to do was that instead of calculating Peclet number like this and calculating the diffusivity of the film missiles like this, why don't we actually try to measure the experimental diffusivity? So for that we did a very simple experiment where we looked at the fluorescence intensity of the wake at a particular location, and we tried to extract diffusivity out of that. I will not go into the details. But once we have that diffusivity value and we compare that with the Stokes-Einstein value, which is what we just used earlier to calculate it theoretically, we find that if I plot the ratio of these, this ratio with different systems, it is actually not 1. Right? Instead, for higher and higher molecular weights of polyethylene oxide, we observed that the diffusivity actually was much larger than the Stokes-Einstein prediction diffusivity. So this is what we call as the breakdown on a continuum approximation, which makes sense because earlier it has been proposed that if you look at the nanoparticle diffusion in a polymeric solution, unless the particle size is big enough to experience the polymeric environment as a continuum, we will not get the diffusivity to be the Stokes-Einstein diffusivity. So the particle size is smaller than the polymer length scale that is present, when the particle will not experience the polymer as a continuum, rather it will move freely through the gaps and will experience a diffusivity which will be much higher than what Stokes-Einstein can predict. And in fact, we calculated the ratio of the length scales for our system, where RS corresponds to the length scale of polymer and A corresponds to the length scale of the missiles. And for higher molecular weight systems, we actually computed that the length scales, polymer length scales, were actually much larger than the missile length scale. That explains why a small missile will not experience the bulk viscosity, rather it will move more freely in the system. So now what we did was that to bring all this information in one place, we proposed that let's not use the same Peclet number where the missile diffusivity is computed using the bulk, the Stokes-Einstein prediction. Rather, let's define a Peclet star where now D should account for the local viscosity which the missiles can experience. And once we do that, we get a very nice result where with increasing Peclet star, now we can see that the persistent length of the droplets is actually decreasing. So this, with this proposed definition of Peclet star, everything fell in place, and this Peclet now is able to capture the increased fluctuations in the droplets trajectory. Then we did one more thing, that we fixed a particular molecular weight and we increased its concentration gradually. So we chose 8000 kDa as the molecular weight, and we increased the polymer concentration to 1 and 1.5. So as expected, for these systems, the Peclet star decreased because we are increasing the viscosity of the system, so droplet speeds would go down, but we are not changing the diffusivity of the missiles because the molecular weight is very high. And what it led to was that in water, we know that the droplets perform these random trajectory, but in high molecular weight polymer, droplets perform these very extremely persistent trajectories. So there is no jitteriness that we have ensured by ensuring the low value of Peclet star, but by choosing a high molecular weight, we have also ensured that the droplets are performing extremely persistent motion. And this is despite, and look at the values, so bulk viscosity is starkly different. In water, the bulk viscosity is just 1 centipoise. In this 8000 K polymer system, the bulk viscosity is 10 Pascal seconds. So it's an increase of 10 to the power 4 order of magnitude. But the local viscosity which the missiles experience is the same, because these are high molecular weight polymer and missile size is much smaller than the polymer length scale. Right? And that, because of that, we are obtaining a regime of very low Peclet number, and droplets are performing an extremely persistent motion. Right? So to further understand this, we decided to let us look at the swimming modes these droplets are adopting. So typically from biological organisms, we know that a swimmer can be either a pusher where it generates a thrust from its rear end, or it can be a puller where it gets pulled from the front end. So E. coli is known to be a pusher, Chlamydomonas is known to be a puller. In 1971, Blake and co-workers proposed that the surrounding flow field of a swimmer can be modeled as a simple squirmer, where we assume the squirmer to be a two-dimensional object generating an axisymmetric flow field, and the surrounding flow field were proposed like this, to which if we take if we apply certain modifications, ignore higher order terms, we'll get the surface flow field to be like this. From here we can calculate a parameter called beta, which now captures the mode of the swimming. So if beta is less than 0, that represents a pusher. If beta is greater than 0, it represents a puller. And if beta is 0, it represents a neutral mode of swimming, which paramecium is known to adopt. So through experiments, PIV experiments, we then capture the flow field around the droplets, and through that we calculated the beta value to identify the mode of swimming. So what we found was that in case of water, the droplets were pushers, so beta values were slightly on the negative side. But in the high molecular weight PEO systems, the droplets were pullers in nature, and the reason was of their high beta value. In fact, we increased the polymer concentration, the beta value become more and more positive, so the droplets were becoming more and more puller. And because of their puller nature, they were able to swim more persistently, because in puller, you are getting flow from the front. So droplet would like to follow that direction, because of that is the direction from which it is getting more and more surfactant. Whereas in pushers, the droplets are getting supply from the sides, so droplets motion is actually susceptible to change in directions. We do also have some understanding behind why at low Peclet number droplets become puller and why at high Peclet number droplets become pusher, but I'll skip this part. I'll move to more exciting discussions. I'll skip that part also. So far we restricted our system such that the viscoelasticity of the surrounding media was not invoked, and that we ensured by making the surfactant keeping the surfactant concentration below a particular value. So if we are restricting ourselves in terms of surfactant concentration below a particular value, the droplet speed, we are also restricting that. Okay. Now what we did was, next, using the same system, we now increase the surfactant concentration to very large values. And the reason being because we wanted to invoke this Deborah number now. So Deborah captures the relaxation time of the surrounding polymeric system with respect to the droplet motion characteristic time scale, which is R by V. So by increasing surfactant concentrations, we have now increased the velocity values to very large values, and hence we are able to increase the Deborah number also. So in previous systems, the Deborah number was kept towards the low values, but now what we are doing intentionally is that we are looking at large values of Deborah and then try to see what happens. So then what we observed was that at Deborah of around 0.2, these droplets do not maintain their spherical shape, rather they get deformed from the rear, if I may play it again, and perform the active motion. So you can probably see that the droplet is deformed from its rear end, so it does not maintain its spherical shape anymore. On calculating, we observe that the capillary number of these systems is still very low, so the viscous stresses are not able to explain the deformation these droplets. So then what we found was that this very beautiful work by Leal and co-workers in 1993, where they observed the deformation in a rising bubble in a polymeric environment. And they explained that that is because of the normal stresses which these stretched polymers are able to generate at the interface of the bubble, which can lead to the deformation. So when the droplet of the bubble is rising, it encounters these polymeric chains, it stretches the polymer chains at its periphery, and towards the end where the stretching is maximum, the polymer chains get deformed to their maximum extent, and that leads to normal forces which can lead to the deformation in the bubble shape. Right? So we believe that the similar mechanism could be at play in our system, although the propulsion mechanism or the mechanism of motion is different, but the physics of deformation could be very similar. So with the help of my colleague at IIT Kanpur, Dr. Naveen Tiwari, we tweaked the model to make it suitable to our system, and we found that there was a very reasonable match in the deformation predicted by the model with our experimental observations that confirmed that the stretching of the polymer chains of the droplet is actually responsible for its deformation. Then we wanted to be even more courageous. We increased the polymer concentration further this time, so with the goal of increasing Deborah number even further, and then we observed something very dramatic, that the droplets get deformed quite dramatically, and they also perform a periodic random zigzag motion. Right? So now These droplets are no longer deformed from the rear end. They have all sorts of different deformations going on, and they also perform a random zigzag motion. To understand this further, we looked at the speed values, we looked at the Deborah values, and we also looked at the deformation index values, and all of them oscillated with a particular time scale while remaining in sync to each other, right? And at a particular cycle of this zigzag motion, we observed that the droplet started with the least deformation. So psi is a parameter which calculated the deformation of this droplet shape. With increasing speed, the droplets become more and more deformed, but the deformation now shifts from, deformation first appears at the front, it shifts towards the center. At this instant, the droplet is maximum deformed. Then the deformation shifts towards the rear, the deformation decreases, and eventually the droplet comes to a minimum speed state where the deformation is also minimum. Right? To understand this further, we again repeated the PIV experiments and tried to identify the mode of swimming of these droplets under different conditions. We found when the droplet is actually deformed from its front, at that instant the droplet is actually in a polar mode. And when the droplet is deformed from its equatorial region, from its along the body, at that instant the droplet is in the neutral state, and eventually when the droplet is going to a state of least mobility, the droplet is becoming more and more pusher in nature. For this we do have some understanding, but that is again in the preliminary stage. It's not concrete yet, so I'm not going to discuss it. But as far as the zigzag motion is concerned, which was very peculiar in nature, we do believe there is an explanation for that. So when the droplet starts, it starts with a pusher mode. At this instant, when the droplet is arrested, the droplet is at the least speed, the droplet is in pusher mode, with that we confirm through PIV experiments. And the pusher mode, the droplet pulls fluid from its sides, because of which the droplet now tries to change its direction. It would like to go in a direction from which it is getting the fresh supply of surfactant. So in this particular case, the droplet can either go towards the right or towards the left. Right? So let's say the droplet decides to take a turn towards the right. It will go through a series of deformations, it will become a puller again, it will become a neutral again, and eventually it comes to a state of becoming a pusher again. Now in this state, the droplet again has to take a decision whether to take a turn towards the right or towards the left. At this instant, what the droplet experiences is the region which was already filled with filled missiles, because when the droplet moves, it leaves a wake of filled missiles in its behind. Right? And because at this instant there is already a wake that is present, the droplet consciously avoids this region because of phenomena called negative water chemotaxis, and the droplet takes a turn which ensures that it steers away from this region, and that leads to sort of a zigzag motion in the droplet. Right? So with this, I would like to thank the funding agencies, my collaborators, and the work which I just talked about is done by an outstanding PhD student named Pratik Dwivedi, and I would like to thank you again for your attention.
In the viscoelastic environment, when you claim that you saw shear thinning induced by the motion of the droplet, not shear thinning, but I mean the alignment of the polymer chains.
The deformation.
Yeah,
the stretching of the polymer chains.
Stretching of the polymer chains. If you were to do the diffusivity measurements there, as you go behind the droplet, would you see an anisotropic diffusivity becoming more isotropic, and will that tell you something about the alignment of the polymer chains?
See, diffusivity of missiles will be same in all these systems, because we are talking about a system where missile size of the order of few nanometers and polymer size is much larger than that. So although the polymer chains are being stretched, we don't expect the diffusivity values to be different at all, because we are not in the continuum regime. These are high molecular weight systems.
So I was just wondering about whether you can say anything about how two of these things interact with each other.
That is actually which one we are trying to do now, but it experimentally is very difficult to have two different swimmers together. In fact, we were successful for the first time to demonstrate that by adding polymers you can get a puller mode also. It was not known so far, but adding two different swimmers is a challenge for us right now. We are trying to think of a way we can do that, but as of now we don't know how to do it.
was curious about this jittery motion that you showed in the beginning.
Yeah.
So have you characterized it, like for example, I mean, it reminds me of fractals, for example. So like, what's the variance or end-to-end distance with time? Is there any characterization of those jittery trajectories?
We have not tried to do something like that. The best we have done is measure the persistent length. But what you say is interesting, and we should definitely look into that as well.
Thank you.
And coming to that, it actually depends on the dimensionality of the system. So what we have observed is that if you take a thinner cell, you will get different kind of pattern compared to a thicker cell, where the droplet can actually go in the third dimension as well.
Yes, but the one that you're showing is in 2 dimensions, right? The one that
All these experiments are in
system
restricted to 2 dimensions only. But I'm saying that the fractal nature that you have talked about can vary with if you change the optical cell thickness as well.
Yeah, the droplets sometimes appear to roll, not slip. So
Can you please repeat?
the droplets appear to roll, and not slip. So is there something else?
What do you mean when you say appear to roll?
Roll, they were rolling on the surface.
These are actually internal recirculations that we are observing. So
Okay.
droplet is moving forward with the help of some internal recirculations. So
Okay.
we would not exactly call it rolling because
Rolling,
we are not
okay,
particles.
Fine. Yeah, thanks.
Yeah, we can take one more question. Rahul, nice talk.
Yeah.
What's the origin of these periodic deformations of the droplet? Maybe I missed that.
You mean this, right?
Right.
Yeah, so for that, our understanding is still preliminary, but we believe this is again related to the Peclet number of these droplets. See, Peclet number in a way captures the area that the filled missiles cover around the droplet. So the Peclet number is high, so diffusivity of filled missiles becomes high. So it can cover more area around the droplet. So if the droplet is more covered by the filled missiles, it will try to avoid the surrounding and try to move in a particular direction, which can give it fresh surfactant supply. So we believe that in all of these systems, we are at high Peclet number, where the droplet will try to move in a particular direction, and it can only adopt it through a puller mode, because puller mode will give it the push from the front. It can go in that direction quickly. And once it starts to do that, because of the flow field that it generates around it, it gets deformed. And that allows the droplet to go through different modes. But it again gets trapped in the same pool of filled missiles again, and the process repeats. But again, as I said, it's a preliminary understanding. We need to do more experiments to confirm this.
Thank you.
Yeah.